So I think we are recording. Right? Sorry about that. Yes, we are recording. Okay, so as I said, I'm just going to do a quick summary in here, but I'll start with the basic thing, why we need group theory, right? For that reason, I need to share my screen again, and I'm going to open this this program. This is actually a program called Mischief. Yeah, I forgot writing this thing down. So it's a program called Mischief. I'm also going to share the source code for this because it's a program that's not actually maintained. So you can only open the lecture notes by using this program, right? So just keep this in mind. So we don't have undo in here, so I'm going to do the undo with Control Z. Can I do undo like that? No. So let me clear this. All right. Okay. So in any case, so the basic idea is symmetry, right? In any case, in physics, the symmetry actually has a very special place because if the laws of physics satisfy some certain symmetries, or your physical system satisfies some certain symmetries, these symmetries have some special implications. Right? One of them is what we call as the Noether's theorem. Which says that for every continuous symmetry, there is a conservation law. So I don't know if I'm going to be able to describe this connection. Sorry about this. I think I cannot do an undo conservation law. Yeah, let me try to. All right, I think I can only erase like that. Sorry. All right. There's a conservation law. So, for example, the translation symmetry, for example, implies that the linear momentum is conserved. If you have actually taken the general physics from me, probably I mentioned that thing to you too. Right? Probably you already know about this. So that's one implication. Another implication is so that's something that we are going to actually cover within that course. It implies, for example, degeneracies or something like that. Think about the hydrogen atom, for example. It has a 1s level and a 2s level and 2p levels. And we don't have just a single 2p level. There are actually 3 2p levels. 3 2p levels, right? These are all degenerate, for example, right? They have the same energy. All right, so somehow the keyboard is not working, but I can do an undo like that. All right. And similarly, right, there are like 3s, 3p, and 3d levels, right? So there is a 3p levels and 3d levels. So there's actually a bigger degeneracy in here. So there's a 4-fold degeneracy in here and a 9-fold degeneracy in here, for example. So all of these degeneracies actually come from the rotational symmetry of the hydrogen atom. So hydrogen atom is a system where all directions are more or less the same. And so as a result, that's one implication of that symmetry, right? And especially in this aspect, of course, we are interested in the implications of symmetries, especially in this course, right? So the rotational symmetry also has conservation implication as well. It implies that the angular momentum is conserved, for example, but it has this kind of an implication too. Okay. In any case, what is this course? This course is actually a systematic way of investigating the relationship between the symmetry and its implications for physical systems. Okay. But to do the systematics, we have to express these symmetries by some kind of a mathematical structure. And in that case, the group is the necessary mathematical structure. Okay. So in that case, we are going to consider the symmetry operations as some kind of elements of some groups, a symmetry group. So basically, we have the construct of symmetry group. Okay, so that's G, and it has some elements, right? So in that case, there's some kind of a list of elements in here. So each one of them is going to be a symmetry transformation. So it's a symmetry transformation. All right. In any case, these transformations should satisfy some certain properties. Like, for example, if G1 is a symmetry of some shape or some physical system, or I don't know, the laws of physics or anything like that, in that case, G1 is symmetry implies that its inverse operation, inverse transformation is also symmetry, a symmetry. So this kind of tells you that if you have a symmetry group, then each of these transformations should also, for each of these transformations, their inverses should also appear in within that set. There's also another thing in here. If G1 and G2 are symmetries, then the symmetry operation that's obtained by first applying G1, so that's function composition in a way, is also a symmetry. So it kind of tells you that within that group, therefore, this composition should also be allowed. And so therefore, the composition of two symmetric transformations is also symmetric transformation. There's one last thing in here. So there's actually something that we actually call as the identity element. So that's essentially a transformation that does nothing at all. That's also some kind of a symmetric transformation. And so therefore, I mean, it should have this kind of an element as well. So that's called an identity. Identity is also a symmetry. I mean, it's a very simple thing, but to be complete, we have to actually include this in there. So as a result, by a group, we mean this. So a group is G together with some kind of an operation. So in here, it is composition, but in some other cases, I mean, for mathematicians, for example, it might be an addition, multiplication, or any operation like that, right? So is a group. So here, O is composition. Sometimes I'm going to call this as the group product. Sometimes I'm going to call this as multiplication because I don't know the difference between these two, these terms, multiplication. All right. Sometimes the symbol is going to change, right? G is a group. So there's a this is a binary operation. Binary operation means that if I take two elements within the group, let's say, then their operation with this operation is going to give you a third element within the group, right? In any case, so if this binary operation satisfies these properties, right? So the first property is that so this operation is associative. So that's the associativity. So that means if I have like G operation with H, operation with K, for example, the two operations between three elements. So in that case, which operation should I start first? Should I do the operation of G and H first and then with K? Or should I do it first like that and then with this? Okay. So the claim in here is that, we are assuming this as an axiom that this operation is associative. So it doesn't matter whether you do the operation like that or like that, you get the same thing. Okay, so that's the first property. Function composition, for example, satisfies this property. Multiplication or addition operations that we know from algebra, that satisfies that property. Matrix multiplication, for example, that also satisfies. So there are actually many examples of such operations that satisfies that property. And so as a result, we have lots of examples of groups from these actually. Second one is the identity. So there is a special element E called identity. So I have to do this undo, right? Called identity, such that the E of G is equal to G and G of E is equal to G. So that's for all G. So it's an element that's in Turkish is called etkisiz eleman, right? So as a function, for example, it's the identity function. It doesn't do anything. It doesn't change anything. So as a result, these are like that. And then for each element, we claim the existence of an inverse. So, right? Every element G has an inverse shown by G inverse such that G operation with the inverse is equal to identity, or the inverse operation with G is equal to identity. Okay, so these are the three basic axioms of a group. So mathematicians basically assume that only these properties hold, and then based on these, they just try to drive the various properties of the groups. So at first we are going to go like that, because this kind of point of view is actually quite useful. But of course, there are some situations where we have concrete examples of these. For example, these are matrices, and it's just a matrix multiplication. So we are going to see these kind of examples a lot. All right. So sometimes, from the last property, for example, you can see that, for example, the inverse of the inverse is the inverse. Inverse of the inverse is the element itself. So if G minus 1 is the inverse of G, then inverse of G minus 1 is G as well, because both satisfy these relationships, right? So these relationships tells us that this is the case. There's another relationship in here. Probably you are familiar with this from matrices, for example. If you have a product of two elements, then the inverse is obtained by taking the inverse of the second element operation with the inverse of the first element. I mean, we are changing the order in here, so that's important, because commutativity is not really valid for some groups. And then we have something like that. So we say that, let's say, if the order of the product is unimportant for two elements, so we say G and H commutes. This is also coming from in quantum mechanics. Perhaps you are familiar with this thing. In that case, we say that the operators commute or not commute if you can change their places and you get the same thing, right? It's more or less the same thing. So we can say that two elements commute. We can say that the group is commutative. Right? Let's say group G is commutative or abelian. Let's just write this thing down. Undo. How undo? Undo. Abelian. It's an abelian group if all elements commute. Right? Elements commute. And otherwise it's non-commutative, non-abelian. So for symmetric groups, we have abelian symmetric groups. So there are some examples of abelian symmetric groups, like the translation group, for example. That's one example. And there are non-abelian symmetric groups like the rotation group. So the set of all rotations, for example, is a symmetric group where the group itself is non-abelian. So two rotations in general do not commute with each other. So if you have like two rotations followed up one after the other, the result depends on in which order we apply the rotations, right? When we talk about the rotation groups, we are going to stress on this. And some properties of angular momentum, for example, comes from the fact that that group is not abelian. All right. I wanted to say something, but I forgot. So about the axioms in here. All right. So there are some special groups like these. For example, if I have X is any set, and functions, for example, you can define functions from this set to itself. So if F is one-to-one and onto. Okay, so that means, like, I don't know, if X contains, let's say, 3 elements, that function somehow associate each point to each point. So this to that, for example, and this to that, for example. So F sends every element of X to every other element, to different elements. And so therefore it also covers it, right? If F is one-to-one and onto, then in that case, the inverse of F exists. So I can then define the inverse in there. Okay, in such a situation, for example, the identity map is basically a map that maps every element of X into itself, right? I don't know how to write this. EI is equal to I for all I. Okay. In that case, if you have like two maps from X to X, I can define, for example, G of F, the function composition. It is basically defined like this. G of F applied on, I said I in here. This is the same thing as first computing F of I, and then computing G of F of I, right? If you remember, that's the convention in here. So in that case, for two functions, I can have the composition like that, right? So composition of two functions, for example, if all of these functions satisfy this property that they are invertible, actually satisfies this group property. There are many examples of these. I'm just going to give you some examples. So X is a set of a set of n objects, let's say. Right? In that case, Sn is basically the functions from X to X, let's say invertible functions. sorry, I don't want to cross this. Sorry about that. So something that's not manageable. So F is invertible. All right. So these are essentially all permutations of n objects. Okay. These are all permutations of n objects actually. So in that case, we are essentially talking about functions which switch each object with another object in a way. I can think of them as functions, and two permutations can therefore be combined by this composition thing. So as a result, if you have two permutations, you just change their places and then change their places with some other permutation as well. So in that way, you can define the composition of two permutations too. So this is called a symmetric group. Symmetric group. So basically, this is a group of n factorial elements. So there are n factorial elements. There are n factorial possible permutations of n objects. Identity is one of them. All the other ones are non-trivial. So we are going to study this, all right? Because this is kind of important, especially for physics. So for example, there's something called the identical particle symmetry in physics. For example, all electrons are the same. We cannot distinguish between them. So as a result, if you have some kind of a physical system and somehow in your mind, if you just permute the places of these n electrons, let's say, in this n electron system, in that case, you're going to have a quantum state which is essentially the same as the original one. All right. So as a result, if you do this symmetry operation, if you permute the places of identical electrons, then you get a configuration that has the same quantum state, right? So therefore, the quantum state remains invariant in a way. So this is some kind of a symmetry, actually. And we can, well, this symmetric group, Sn, is the group that we use to study that symmetry, right? That's what I should be saying here. Okay. So X might be the set of R squared. And in that case, I'm going to call this O2. Let's say, I don't want to use the set notation in here. Sorry about this. These are basically the rotations on the plane, including the reflections. These are also operations, symmetry operations, which are considered as a map. So let's just show the plane, for example, the set R2 is a plane like that. So there is an origin in here. So this is a map that essentially transforms, well, maps every point to another point in here. But you can think of this as a transformation that maps every vector into another vector. Another vector like that. So let's just call this as A prime. There is a rotation in here. So a rotation basically can be thought as a transformation from A to A prime. Okay. So as a result, this is also a symmetric group because the composition of two rotations is a rotation and a reflection is a rotation and things like that. Right? And what's more is that we can kind of express this rotation as some kind of a matrix product too. So in that case, I have a vector A. I can express the vector by its components. So that's essentially the vector A. This is transformed to vector A prime which I'm going to express as a matrix, for example, with components ax prime and ay prime, I can write this thing down as some kind of a 2 by 2 matrix multiplied with this components of the original vector, right? So we have like a 2 by 2 matrix in here. I'm just going to write it down like that. So this is called the rotation matrix. So basically A prime is obtained as R multiplied with A. So in a way, a rotation is actually a map on the two-dimensional plane. So therefore it's a function, but I can express this function as a matrix. All right. So basically every rotation in 2D can be thought as a 2 by 2. I'm going to call this as the orthogonal matrix. Like that. So as a result, if you have a composition of 2 rotations, that basically corresponds to a matrix multiplication. So let's say it like this. So A is first rotated by R into A prime, and then it's rotated by S into A double prime. So all of these vectors should have the same length, right? So in any case, A is first transformed into A prime, which is given as R times A. But A prime is transformed into A double prime, which is S times A prime. But this can be expressed as SR times A. So therefore, the whole transformation is the composite transformations from A to A double prime, which is given by the product of S and R multiplied with R. Right? So here is basically this is the first rotation. So SR is basically the matrix multiplication of S and R, right? So what we do is really a function composition, but I can think of this function composition as some kind of an algebraic operation between matrices. All right, in that case, the elements of the group are basically matrices, orthogonal matrices, and the operation is the matrix multiplication. Okay, there are many situations like that. So there are some groups, for example, where I can consider the group operation as a multiplication of some complex numbers, for example. Right? There are these kind of examples. I don't know. For example, the real numbers together with the addition is a group. So that's called the translation group. Translation group in one dimension. I can think of the elements of that group as some kind of functions that basically translates points in space. I can also think of them like that. Or I can simply think of them as just numbers, and I'm just adding up these real numbers, right? There are multiplicative groups like these. Real numbers where I subtract, for example, 0 together with the multiplication is a group. This is like a scaling group or something like that. This also has some kind of symmetry implication. Some of the symmetric groups that are used in physics actually. So scaling is a symmetry for some physical systems. We can have like the set of integers together with addition. Right? It's not just all numbers, but only the integers, for example. This is also a group. So in this case and in that case, real numbers and the integers with addition, 0 is the identity element. So that's the discrete translation symmetry, the discrete translation group. Okay. I mean, I can give many examples in here, but like most of these examples have some physical application, right? So, for example, the discrete translation group is something that's used in solid-state physics. There's also a three-dimensional version of that discrete translation symmetry group, right? Normal translation group is used in particle physics, quantum physics, and whatever. I mean, that's actually one of the nice groups. And it's also a group that's quite easy to analyze. The rotation groups are actually a little bit complicated. So we can actually, I mean, for all of these examples, we can find some kind of a physical situation where these are really symmetric groups and there are corresponding symmetric transformations, right? But most of the time, when we talk about these groups, how we define the group is not really relevant. It appears that that's not really relevant. So, for example, in the discrete translation, there is actually a translation amount, which is some kind of a distance, like 1 angstrom, for example. But here, I just took the translation distance by 1 unit, for example, right? By number 1. The fact is that it actually doesn't matter because both groups have more or less the same structure, right? So what the distance is actually is irrelevant. And how we define the groups are also kind of irrelevant. In that case, we talk about this isomorphisms between two groups. So if you have like a group and another group, sorry about this. And H star, for example, these two groups are isomorphic if, I think mathematically we say that if there's a one-to-one correspondence between elements. So let's say it like that, right? If there is a one-to-one correspondence between elements of G and H. So I'm just going to show it like that. So if there's an element in here, there's a corresponding element in on the other side. So if I just consider these as sets like that. So for every element in here, there's a corresponding element H prime in here. So you just form this kind of a correspondence. This is in a way a function actually, but I'm just going to keep it short, right? So G prime, G double prime, for example, corresponds to H double prime, and triple prime corresponds to H triple prime, for example, right? We say that they are isomorphic if the operations also correspond to each other. So that means like if, for example, G operation with G prime operation with G double prime gives you G triple prime, then the same is also true for the corresponding elements in H. Okay. So in that case, we just say that the groups are isomorphic. So that's the notation that I'm going to use. Sometimes I just forget about the group operation and we just say the same thing for, sorry about this, it's not K, this is H. So that's H. We say that these two groups are isomorphic. So isomorphic means the groups are the same, but the operation perhaps or the mathematical details might be different. So one might be a matrix group, the other one might be, I don't know, some numbers or operations in, I don't know, some kind of a function in some complicated space perhaps, right? So, for example, the permutations, sometimes we would like to express the permutations as a matrix group with some things called permutation matrices. So as a result, I can express the group in a mathematically in a different way, but these two are still the same groups, right? Even though the elements and the mathematical meanings are different and the operations appear to be different, they are still the same group. So for us, for physical implications, the structure of the group is the most important. So therefore, this isomorphism is something that I'm going to rely on. So that's going to be an important part of what we are going to do. So as a result, we need to say something about the structure of the groups. So for example, whether the group is an abelian group, commutative group, or non-abelian, that's one of the important things. It appears that if the symmetric group of a system is not abelian, if they are not commutative, in that case, we have the degeneracies, right? I mean, that means that if the symmetric group of a system is abelian, that system probably has no energy level degeneracy. So all levels would be non-degenerate. That's what it says. But if the symmetric group is non-abelian, then depending on the structure, we have some degeneracies, all right? So at the end of the semester, we are going to give some examples like that. And so for that reason, for us, the structure of the group is the most important. All right, so unfortunately, I couldn't finish this. I mean, let's just do it like this. So let me try to arrange some other hour, perhaps during the weekend, 1 hour perhaps. Then I can summarize all the rest, but it has to be a quick summary. This is more or less the introductory part, all right? So there are some other parts that I have also done. So let me go through this quickly. So I think we can do this quickly on Saturday, for example. So I'm going to send you a message and let's just do this, right? So otherwise, I mean, I have to finish this because I have to give this tablet to another person. And so as a result, I have to do it quickly. So I don't know if you have any questions. Let me stop this first.